Hello everyone. Today we'll be going through section 4.3 of Pure Math 2. We'll be looking at the derivatives of exponential functions, specifically e to the x and e to the f of x. We'll look at the derivatives themselves, we will prove them, and then I'll go through a quick example finding a more complex derivative of an exponential function. Now starting off, we're going to look at the derivative of e to the x. If we have a function, y being equal to e to the x, the derivative of y with respect to x is also just e to the x. And this is very, very unique. It's the only function that acts this way. In fact, one of the very definitions of the exponential function is that it is its own derivative. It's very, very interesting. Secondly, looking at a function y being equal to e to the f of x, the derivative of this will be such that y prime is equal to f prime of x multiplied by e to the f of x. So you can see that this is similar to our first derivative here, in that our exponential term itself doesn't change. We still just have e to the f of x. We're just simply multiplying by f prime of x at the same time. And this holds for our first function here, because the derivative of x is just equal to 1. An example of a function we could differentiate using this would be y is equal to e to the power of 17x squared minus 9. In this case, f of x would be equal to 17x squared minus 9. We will prove the derivative of e to the x using the first principles of differentiation, and we will prove the derivative of e to the f of x by using the chain rule. Now, I would like to prove the derivative of e to the x by first principles. Consider some function y being equal to e to the x, and we will consider a small change in the value of x, called delta x. We'll consider what happens as delta x approaches 0. We'll consider that dy over dx is equal to the limit as delta x approaches 0 of y2, which is going to be e to the x plus delta x, subtracted by y1, which is just e to the x, divided by x2, which is x plus delta x, subtracted by x1, which is just x. The x's in the bottom cancel out, and to simplify the top, we will factor out our common term e to the x. This is going to be equal to L. Now, L, in this case, is just going to be the shorthand I'm going to use for the limit as delta x approaches 0. These two mean the exact same thing. L of e to the x times e to the delta x subtracted by 1, divided by, our x's cancel out, so this is just going to be delta x. Now, the convenient thing about this e to the x term here is that it doesn't contain delta x, so we can move it outside of the limit. This is going to be equal to e to the x times L of e to the delta x subtracted by 1 divided by delta x. Now, this limit, it can be fairly tricky to do. So I'm going to go through two separate methods you can use to do it. First is just using a table of values and seeing what your value approaches. And the second will be a little bit more rigorous, using some algebra, specifically using logarithmic functions and some substitutions. So we're going to let this term inside our limit here be set as some function g of delta x. Then what we're going to do is we're going to insert smaller and smaller values of delta x into our function g of x here. a g of delta x here, and we're going to see what happens to the value of the function as a whole. We're going to start off with g of 0.1. And evaluating this on the calculator ends up giving the result of e to the 0.1 minus 1 divided by 0.1. And this ends up being equal to 1.0517, and then the decimals continue from there. Let's consider taking this down by a degree of 10. G of 0.01, inserting this into your calculator, you would end up with 1.00501, and then this decimal would continue. We'll take this down another degree just so we can be absolutely sure, but it already appears that as our value of delta x is approaching closer and closer to 0, the value of the function as a whole is getting closer and closer to 1. Inserting 0.01 into this, we end up with 1.00050016, and then this continues on as well. We can pretty much infer from this that this limit, as delta x approaches 0, is going to be equal to 1. And if this limit is going to be equal to 1, then we know that dy dx is going to be equal to e to the x multiplied by 1, which of course is just e to the x. Now, for the second, slightly more rigorous way of proving that this limit is equal to 1, we're going to consider this entire limit as being some lambda, just so we can write it down a little bit more easily. We're also going to consider our delta x as being equal to some h. This, in and of itself, doesn't really have much significance, it's just that h is much faster to write than delta x. Then we'll consider that our lambda is going to be equal to the limit as h approaches 0 of e to the h minus 1 divided by h. Now, for this, we're going to use a bit of substitution. We're going to let some variable u be equal to e to the h minus by 1. Now, if we're going to be using substitution here, we need to change the variable in our limit. So we need to consider what happens to u as h approaches 0. Well, as h approaches 0, we know that e to the h is going to approach 1. E to the 0 is equal to 1, of course. So e to the h subtracted by 1 is going to approach 1 minus 1, which is just going to approach 0. So u is also going to approach 0 in this case. Now, we also need to know h in terms of u. We can rearrange this to say that e to the h is going to be equal to u plus 1, and then we can take the natural logarithm of both sides to state that h is going to be equal to ln of u plus by 1. Now from here, we can substitute all of this into our original limit, lambda. We can say that lambda is going to be equal to the limit as u approaches 0 of u divided by the natural log of u plus by 1. We can change this fraction around a little bit. We can say that this is going to be equal to L of, so we're doing the exact same thing here with L. Still just means the limit as u approaches 0. We can say that this is going to be equal to L of 1 divided by 1 over u times the natural log of u plus by 1. Of course, in this case, this 1 over u in the denominator would translate to just being a singular u in the numerator. We've just switched around where it is in our equation a little bit. And the reason why is because we would like to use some logarithm properties here. From the power rule of logarithms, we know that log of a to the power of b is the same thing as b times by log of a. So we can use that here in reverse to state that this is going to be equal to L of 1 divided by the natural log of u plus by 1 to the power of 1 over u. Now, we have a little bit of a fancy function over here, u plus 1 to the power of 1 over u. We want to consider what happens to that as u approaches 0. So let's consider a separate limit. We have the limit as u approaches 0 of 1 plus by u to the power of 1 divided by u. Now this is very, very similar to the limit definition of Euler's number e. And it would be very convenient if we could have e, because we know that the natural log of e is just going to work out to be equal to 1. I'm going to suggest another substitution here. Let's use u is equal to 1 divided by n. Now, we can make n the subject of this equation, say that n is equal to 1 divided by u. And as u approaches 0 here, this fraction will approach 1 divided by 0, so our denominator gets smaller and smaller and smaller, which means our fraction gets larger and larger and larger. So n will approach infinity. We can now rewrite this limit as being the limit as n approaches infinity of 1 plus by 1 over n to the power of n. And this is our exact limit definition of e. That's very, very convenient. We can now take our limit, lambda. We can state that this is going to be equal to 1 divided by the natural log of e, which of course is going to be 1 divided by 1, which is of course just going to be equal to 1. We can then state that our derivative of y with respect to x is going to be equal to e to the x times our lambda, which will just be e to the x times by 1. E to the x times by 1, which is equal to e to the x. Perfect. Now, from here, I would like to take a little look at the derivative of e to the f of x, and how we could actually go about finding this. E to the f of x, where we will state that y is equal to e to the f of x. So for this function, we're going to want to make a substitution stating that u is equal to f of x, and then y is going to be equal to e to the u. We can differentiate both sides with respect to u to find that dy over du is going to be equal to e to the u. We can differentiate this function up here with respect to x to end up with du over dx being equal to f prime of x. And then we can use the chain rule, which states that dy over dx is going to be equal to dy over du times du over dx to find that our derivative of y with respect to x is going to be e to the u times by f prime of x. which of course is going to be equal to f prime of x times e to the f of x. Now, from here, I'd like to just look at a quick example of this in use. We're going to differentiate some function y being equal to e to the x squared. E to the power of e to the x squared. We're going to state that e to the x squared is equal to some u. Then we're going to state that x squared is equal to some w. And from here, we can start doing a couple of things. Firstly, we can state that y is going to be equal to e to the u. We can find that dy over du is going to be equal to e to the u once again. We can find that dw over dx is going to be equal to 2 times by x. And we can state that u is going to be equal to e to the w. So we know that du over dw is also going to be equal to e to the w. From here, we can find du over dx using the chain rule. Du over dx is going to be equal to du over dw multiplied by dw over dx. And this, of course, will be equal to 2x multiplied by e to the w. And now that we have du over dx as well as dy over du, we can use both of these to find our derivative of y with respect to x, which is going to, of course, be dy over du multiplied by du over dx, which is going to be e to the u times 2x times e to the w. And now, substituting both of these into our equation, this will be equal to e to the x squared multiplied by 2x multiplied by e to the power of x squared. Now, of course, you could simplify this further. I don't have much space here, so I'm just going to draw an arrow going up here. You can say that y prime is going to be equal to. We can combine these two terms, these two exponential terms, to say that this will be e to the x squared, and then this whole thing plus by x squared. And then this will be multiplied by 2x.